You got it? Thanks. Dearly Father, we thank you for today. I thank you for these students. We thank you for the weekend just completed. Just pray that you just help us to just use this time wisely, Lord, to glorify you and what we do here, Lord. We just thank you for your grace and mercy for us each and every day, Lord. In your name I pray. Amen. Okay. So I want to talk to you about the closed set test. And so the closed set test just it goes back to the start of our discussion, which was we have some function. Let's say a function of two variables for a second on some domain of consideration. And we want to find it's where it's minimized and maximized, right? So here's the rule. And here we're assuming, I'm going to assume that D is a closed set, which just basically means that the boundary of D is a subset of D for us, okay? It has edges, all right? The edges aren't fuzzy. So here's the algorithm. Step number one is you look for local extrema inside D. So you might say in the interior of D. Where do you find those? Where do you find local extrema? Well, that's a place where the gradient of f is equal to 0. So we look for those critical points, or I think your text calls them stable points, right? That was what your question was about, how to find those. So we'll get to that. And then basically you catalog them, right? Make a list of all the interesting points you find, and find the value of the function at each one of those points. That's step number one. Find f of c for all such points. And just to be clear, in the interior of D. And then step number two, investigate f restricted to the boundary of D. So you take the function and you look at it, how does it behave on the boundary curve? So I don't know what it looks like. This could be, D could look something like this. You could have some holes in it, right? And so the boundary of D in this case is that whole edge, right? Maybe you've got, like, this is a critical point. This is a critical point, right? And then as you investigate the function, on the boundary, maybe you find that, this point right here is the minimum on the boundary, and maybe this is the minimum or maximum on that boundary, etc. You'd find some special points on the boundary where you get minimum or maximum. Now, how would you find the special points on the boundary? What would you use? What? Use the method of Lagrange multipliers? Or you could just straight up find a parameterization of the boundary curve and look at the function in those terms. And then what do? You find those values, right? F of c, in my picture, f of c3, f of c4, etc., right? And then 3 is you conclude by picking winners and losers from steps 1 and 2. Does that make sense? That's the big picture of what we're going to do. Let me find a quasi-reasonable example. Was there a question? I was wondering what f of c, what is it in the block? f of C4. I'm just numbering them like 1, 2, 3, 4. Just to give them a label. 5. I'm going to make up a new example. Actually, it's a twist on an example I have in my notes. The objective function we're going to look at is f of xy equal to x to the fourth plus y to the fourth minus 4xy plus 1. Now, this is example 5.4.3 on page 266 of my notes, but I do it for a different region there. Again, example 5.4.3. But I'm going to twist it a little bit. And here's what I'm going to do. I want to find the extrema of this on a triangle. Well, not quite a triangle. Let's say kind of like a snow cone. On this region. Let's say that this is D. And so what I'm going to do is say that this is a circle, half of a circle of radius 1. So this point here is 1, 0. This point here is minus 1, 0. And I'll tell you what, I'll make the this point down here will be minus 1, comma 0. Oh, other way around. So this is the D. So let's go to it. First thing we got to do is try to look for those so-called critical points, right? So that goes back to your question. How do you find those? The answer is different for different problems, but certainly you have to calculate the gradient. So what's that here? And so we set that equal to 0, 0 to look for critical points. What does that give us? That gives us 4. Well, you get rid of the 4's, right? So you've got x cubed minus y is equal to 0, and y cubed minus x is equal to 0. We need to solve those simultaneously, right? Because we need both of those equations to be true at a critical point. So, I don't know. I guess I'm going to take the first one and solve for y, because that's pretty easy to do, right? Y equals x cubed. And then I can plug that into the second equation. What do I get? So star implies what? X to the ninth minus x is equal to 0. Which is what? This is actually x times x to the 8th minus 1 is equal to 0. What did I do? Oh, okay. Do you have any questions about mission 5? All right. There's no one to complain now. Oh, man. I say that in the friendliest way. I enjoy her complaints immensely. Let's see here. Hey, this is the difference of perfect squares, yes, no? So that is x times x to the 4th minus 1 times x to the 4th plus 1. Can x to the 4th plus 1 be 0 for any real value of x? No, certainly not, right? It's a sum of two positive, well, one's positive and one's non-negative, right? X to the 4th could be at the smallest 0. So the last factor there is never 0. And, oh, but this can break down further. Oh, but we can break that down further. Now, I'm just writing the last two factors for effect, but you could safely omit the x squared plus 1 term and the x to the 4th plus 1 term once we found them, because you know you don't get solutions from them, right? So really, the rubber hits the road on these ones. Those are ones which actually have real solutions that give you 0, right? So our three critical points then, we got ourselves x equals 0, x equals 1, x equals minus 1. And correspondingly, y is equal to what? 0, y is equal to 1, y is equal to, it's kind of funny. The y's are identical because when you cube those numbers, you get back the same numbers. That's just a quirk of this example, right? Funny. So let's see here. Make a list of our values. So we got point value. So I'm going to plug in what? F of xy equals to x to the 4th plus y to the 4th minus 4xy plus 1. And what are my points? I got the origin. I've got 1, 1. And I've got, looks like minus 1, right? Zero, 0 gives me what? 1. And then at this point, we should be like, wait a second. I want to be lazy. I don't want to calculate stuff I don't need to calculate. So what should I say even? Yeah, right? 1, 1 is where? It's up here. Where's minus 1, 1? It's down here. So the answer here is, who cares? These are outside D. They're irrelevant. Just like in Calculus 1, when you do the closed interval method, right, you only consider critical points that are within the interval you're considering, right? So then what? So all right, we found our one local extreme, and now we're going on to step number 2, investigate the boundary. Can I erase this, or are there any questions about this? So the answer to your question, you're asking me, how do you find the critical points for an example? The answer is you carefully calculate the gradient, and then you try to simultaneously solve both fx and fy being 0. Factoring's your friend. Substitution's your friend, right? Be careful not to leave out cases. If you divide by x or y, that means you've automatically assumed x or y is not 0, right? So be wary of division. Factoring is usually safe. I mean, if you do it right. Okay, so the boundary. The boundary has how many pieces? It's got 1, 2, however you want to number them, but there's 3 pieces to the boundary, right? So piece 1 is what? I'm going to use the parametric approach here. So that's a unit circle. So I can say x is equal to cosine t, y is equal to sine t, and it looks to me like 0 is less than or equal to t is less than or equal to pi, right? That will cover the 1 curve. Do you agree? So to look at f restricted to the first part, I don't know, I need to, whatever you want to call this thing, let's call this thing G1, because this gets to be annoying to write. So G1 of t is the value of f on the 1 curve. What is that equal to? F of cosine of t, sine t, right? What is that? Oh, just got real, didn't it? All right, so cosine to the 4th plus sine to the fourth t minus 4 cosine t sine t, right? Plus 1. Man, if I'm going to differentiate this, I'm just going to go ahead and use my trigonometry knowledge and rewrite that as minus 2 sine what? 2t, right? Now I don't need to do the product rule. I may regret that though. No, I'm gonna resist the temptation because I'd like to analyze sines and cosines. All right, fine. There you go. That's a function of one variable. How do you figure out where that's minimized or maximized? So we're looking then, check it out, we're looking at g1 of t on what? The closed interval, 0 to pi. How do you minimize or maximize that? Remember calculus 1? We look for critical points, and then we check the endpoints. What are the endpoints? 0 and pi, right? So if you plug in anyway, let's look for critical points. So we're going to look for g1 dt, which is what? 4 cosine of t minus sine t, right? Plus 4 sine t. Oh, I'm sorry. What am I missing? Kind of important. Cubed, right? Chain rule. Sine cubed t cosine t. There's a minus. No, there's no minus in the second one, right? Okay. And then what? Over here, we get plus 4 sine squared t minus 4 cosine squared t. All of that's equal to 0. What should we do? When we're solving equations, factoring is our friend, yeah. Oh yeah, if there's a mistake, please tell me. Oh, but I'm missing a. That's not quite the same either. Not an entirely crazy idea. If I was to take you up on that, I'm missing a 2 cosine squared t sine squared t that you want. I mean, I totally endorse your idea. It just, we're missing this term, right? Because So yeah, alternatively, I could work with this as being 2 minus 2 cosine squared t sine squared t minus 4 cosine t sine t. Hey, that's pretty slick. That ain't bad. That ain't bad at all, actually. That's you can rewrite that in terms of sine 2t alone. Yeah, the clever solution is often the easier one. The question, though, is would we see it? So this, I'm missing, I need a 4 there to make that sine 2t squared. So this becomes 2 minus 1/2 sine squared of 2t minus 2 sine 2t, if I haven't made a mistake. And we could go down that path. That might be easier. Unfortunately, well, let me try where I was going. The advantage of what I'm doing, of course, is it doesn't require us being clever. I would argue what I was doing in red is somewhat clever. Pretty clever, right? Okay, so is there anything common to all these terms? 4. That's a good point, actually. So, let's see here. You got cosine. We've got cosine cubed t sine t plus sine cubed t cosine t I'm not doing anything. Sorry, let's try to make a simplification there. I guess we can convert. Can we convert all of these to either sine or cosine? So cosine squared is what? It's 1 minus sine squared, right? I'm not sure if that's helpful or not. It's something I could do. But I've still got... Tell you what, let me try. Over here I've got a cosine t, sine t common. So if I factor that out, this gives me what? This gives me cosine, or rather minus cosine squared t plus sine squared t, right? And divide by 4. 4 is dead to us. Okay. So the 4 is dead to us, and then, hey, check it out. Plus, minus, hey, factoring by grouping. Woohoo, hey, check that out. Notice that this term and this term, they're the same. So we can rewrite this as sine squared t minus cosine squared t times cosine t sine t plus 1, right? I have this nagging suspicion that Lagrange multipliers would have been way easier on this. Now, what happens, right? Well, this is what? This is sine t minus cosine t times sine t plus sine t plus cosine t, right? Times, that's really 1 plus 1/2 sine 2t. And those you can solve. Is sine t equal to cosine t on the interval 0 to pi? 0 to pi. Here's sine. Whoop. Here's cosine. Right? Is sine t equal to cosine t between 0 and pi? Well, 0 and pi is where? That's 2 pi. Pi is here, right? So, of course, we get this intersection right here, right? So this has a 0 of t equal to what? Pi over 4. And how about, is cosine t equal to minus, is sine t equal to minus, sine t plus cosine t equal to 0 anywhere? 3 pi over 4, it's like over here. If you add them together, you get 0. Yeah. So 3 pi over 4. How can I see if the other thing is 0? Well, let's solve it. 1 plus sine 2t divided by 2 equal to 0 gives me sine of 2t is equal to minus 1/2, which suggests to me that 2t is equal to what? Indeed. I'm just trying to make sure that what led us to that wasn't wrong. Yeah, so there's no solution. Woohoo! Cool. So that factor is actually, oh, of course. Well, yeah. The only way this could possibly be 0 is if one of these was minus 1 and the other one was 1. But sine and cosine are not simultaneously 1 and minus 1, so there's no way you could get that to cancel out. That makes sense. So pi over 4 and 3 pi over 4. In other words, we have found actually interior maxima possibly 1 here, possibly 1 here. All right? And then, of course, we also need to check 1, 0, and minus 1, 0. Those are four points we should check on the basis of 1. So let's make a list here. F of minus 1, 0, f of, let's see, that would be minus 1 over root 2, 1 over root 2, f of 1 over root 2, minus 1 over root, oh, excuse me, just 1 over root 2, 1 over root 2, right? And f of 1, 0. What are the values of those? I can do the easy ones. This, 1, 2. 2. Okay, I got those. How about the other ones, though? 1 over the root 2. 1 over root 2 to the 4th power is what? It's a half times a half. It's a quarter. So I get a 4th plus a 4th, which is a half. Half plus 1 is 3 halves. 3 halves minus 4xy. Well, that's 4 divided by 2. That's minus 2. But it's plus 2. So 3 plus a half. I think 7 halves. I think this is 7 halves. And I think the other one is plugging in a half and a half. 1 over 2, 1 over 2. Again, I get a half plus a half minus 2 plus 1, which is minus 1. 1 minus a half. Excuse me, a half minus 1. I think it's minus a half. Do you guys agree, disagree? I'd appreciate you checking me on this. All I'm doing is plugging in the points we found from the critical point analysis back into the function to see what the actual values were. Would this have been easier to do with Lagrange multipliers? Maybe. I don't know. Want to try it? Can I erase? You already got it? Okay. Now, if we do Lagrange multipliers, we might accidentally pick up some solutions we don't care about, right? Let's see how we would have used Lagrange multipliers for the upper piece. How about this? Our constraint would have been x squared plus y squared equals to 1, right? And so we would have been looking at the gradient of f equals to lambda gradient of g. The gradient of f I have erased, but it was 4x cubed minus 4y cubed minus 4x equals to lambda times, well, 2x, 2y. Let's see here. So that would give me 4x cubed. I think it's probably going to be easier. I guess we can, what can we do? If we're willing to give up on the 0 solutions, right? If we want to look for solutions where x and y are not both 0, we can divide by x, solve for lambda both of these. So lambda is like 2x cubed minus 2y divided by x. And this gives me lambda is 2y cubed minus 2x divided by, yes, tell me what's wrong. Yes, thank you. Indeed. See, my experience with Sesame Street should have told me that much. It didn't belong. It's not like the others. Let's see here. This is divided by y then. Then, of course, we can set these equal and see where it takes us. Where does it take us? It takes us to 2x cubed minus 2y divided by x is equal to 2y cubed minus 2x divided by y. Oh, that's pretty cool. Look at that. Oh, that's nice. Cross multiply, you get 2x cubed y is equal to 2xy cubed y. Because when you cross multiply, on the one side you get, oh no, it's not quite that. I'm an idiot. I thought the other terms canceled. I'm running out of room here. So fine, 2x cubed y minus 2y squared is equal to 2xy cubed minus 2x squared. Yeah, there's a 2. Got enough 2's to go around here. X cubed y minus y squared equals to what? Xy cubed minus x squared. Well, yeah, we'll do that. So you got x cubed y plus x squared plus xy cubed minus y squared equals to 0. If factoring by grouping happened in the other approach, it probably should happen in this approach as well. Yeah.
Shouldn't xy cubed be negative in your last?
Thank you. Was that it? Yeah.
Isn't that solution true whenever x equals y?
Yeah. That's a good point. X equals to y is a solution to this. But I think that falls into the category of clever. Which isn't bad. I mean, if you see something like that, you see something, right? I mean, if you see something, say something. I have no problem with that. I think, so on the basis of that, I expect we can factor out y minus x. Let's see if that's true.
No, you can factor out an x squared from one grouping and y squared.
Look at this. There's xy, x squared minus y squared plus x squared minus y squared. Now do you see how to factor it? So there you go. But of course, x and y can't be 0 because we already lost the right to think about 0 back over here. So you either have x equals to y or x equals to minus, y equals x or y equals minus x. And so when you look at the constraint curve, you pick up 4 solutions, but only these 2 are relevant to us, right? Because we're only considering this part of it. So we find the 2 solutions we found before with the other method. Yeah? No, we found 2 solutions. We found the pi over 4 and the 3 pi over 4. That was the term that we had 1 plus 1/2 sine of 2t. So that factor didn't correspond to any solutions in the critical points for G1. In the same way, this xy doesn't give us anything legitimate here. But it's the analog in this method, yeah.
Actually, xy plus 1.
Oh, yeah, and thank you. That's even, then the analogy is complete then, isn't it? Yeah, funny.
So x times y.
So I don't know, what do you think? Is it easier to do sines and cosines, or is it easy to do Lagrange multiplier algebra? This is easier? Okay. Personally, I am more at home with the sines and cosines for this kind of thing because I've done battle with them before. So, whatever. I don't care which one you use as long as you use one and you're aware of the fact that you need to do one. So we're not done yet. We still have 2 and 3. I should have warned you. The examples here require a certain amount of patience. It's fine. I can work over here. but I'll give you guys a second to catch up with me. So I think a Lagrange multipliers is not a great method for 2. I could be wrong, but I don't. Lagrange multiplier. How do you get a line from? What would you do? I guess you could run Lagrange multipliers on, like, what would it be? Y equals to, you need y equals minus x, right? So you'd have to run Lagrange multipliers on your constraint being like y plus x equal to minus 1 or something like that. I mean, you could do that, but I typically, for something like 2, I will go with the parameterization of the line segment, which is what? How about minus 1 plus t? And what's y equal to? Do you agree? And that should be for 0 less than or equal to, does that work? If you plug in t equal to 0, we get minus 1, 0. If you plug t equal to 1, what do you get? 0 minus 1, right? So there you go. There's the parametric equations for the line segment. And so let's let g2 of t equals to f of t minus 1 comma minus t, which is what? T minus 1 to the 4th plus t minus t to the 4th, which is just t to the 4th, minus 4, but I'm going to, minus minus going to be plus, so I get 4 times t minus 1 times t plus 1. You know, this example is kind of hard. Anyway, I mean, you see a closed interval problem with a triangle on it. It's a 20-minute problem at a minimum for the most part. I mean, if you actually flesh out the details, these take a while. Uh-oh, I was looking. Sorry. You know, this is a lovely building and all, but it really would be nice if they put some clocks in these rooms. 3:59. Oh my goodness. Tick tock, tick tock. So then you have to find the minimum maximum of this between 0 and 1, yeah?
Isn't it supposed to be negative, multiplied by negative t or no?
Well, right, but there's a minus in the formula, and there's minus here.
Okay, yeah,
So then I'm not going to have enough time to do all this, but basically, beyond this, you calculate what? dg2 dt equal to 0, and see if there are any minimum maximums there, right? So you find if there are any where is it largest and smallest on that line segment. And then step 3 is what? Do the other line segment, right? So which is from where? From 0 minus 1 to 1, 0. So this would have equation x is equal to t, y is equal to minus 1 plus t, 0 less than or equal to t less than or equal to 1. Does that work? Plug in 0, I get 0 minus 1. Plug in time 1, I get 1, 0. Good. And so that will give us g3 of t, which will be defined as the restriction, right, of f to this line segment. So it's going to be f of t comma t minus 1. Which by symmetry has to have the same min-max structure as the other line segment, right? Because x and y appear symmetrically in this formula. And you can see that the formulas for x and y are the same here too. So whatever you find as min-max in step 2 has to be reflected in step 3, although at different points. But anyway, same song and dance. You calculate t to the fourth plus t minus 1 to the fourth. Now this time, minus 4t times t minus 1. There you go. The minus doesn't, plus 1, yeah. Now, I know we didn't have enough time to work out all the details of step 2 and 3, but do you guys see the big picture here, how we do these? Now, I can spend another, hour of class working these kinds of problems. If I had some shorter ones, I might have some of the notes here. Let me see for a second. The one in the notes is what? It's kind of like this, but it's on a different, the region of consideration is slightly different. Let's see here. Eventually I will find that. Here it is. So this one I did for the half disk, right? So instead of doing an ice cream cone, I just did the circle with a diameter. And did I have? Oh, I made it more interesting, right? Actually, it's not quite the same because I made the circle have radius 2, right? And that made 1, 1 actually be inside the circle. That's the difference, right? And but the edge, it's still a hassle. But here it is down here. To analyze the function on the edge, what I do is I just, I parameterize the line segment from minus 2 to 2 with x, I think, in this case. X equals to x, y equals to 0. So the function just restricts to x to the fourth plus 1. And you can easily see that 17 is the maximum value on the edges, at endpoints of the diameter, and then at the top of it, g of 0 is 1, which is the minimum on the half circle, on the diameter. And then I parameterize the half circle and work through algebra, which is very similar to what we just did, right? Look familiar? Yeah. And then I have them all. I have all three. I have the interior of the half circle. I've got the curved part. I've got the diameter. And then I can see of the 9 possible external points, the minimum value is minus 1. It's attained at 1, 1. Maximum value of 19 is attained on the boundary at 2 places, those 2 points. And this graph kind of illustrates what was going on. So here's the output of that x to the fourth plus y to the fourth minus 4xy plus 1 function as you feed it values from like a half disk. Its minimum is down in there, and its maximum ends up on these edges somewhere. Right there. You can see it. But now, example 5.44 is probably a better test question, although it's kind of boring. Or to quote my son, boring. One of his sayings. Although my favorite thing that my son said yesterday is like, I go upstairs. They're fighting like cats and dogs, right? I'm like, what's going on? And Isaac's like, Daniel poked me in the back. I'm like, okay. Daniel's like, well, Isaac poked me in the back first, and remember in the Bible where it says you should do to others as they do to you. So I poked him in the back. Not what it says. Definitely not what it meant. But he was trying to support his actions. Yeah, maybe he's Muslim. I don't know. All right, so, oh, I'm sorry, did I say that? Let's see here. So this one's easier because the gradient of f is a constant, right? So you can just, this is a much better example of a test question of this kind of stuff. Obviously, this one, if we had 4 hours for a test, great, but I do think it's important to see a harder example like that, and now you have. So tomorrow, I will answer your questions about the mission, and if you don't have enough, we'll start integration. Woohoo! Thanks, guys.